It's great to be here in Riga. My name is John Ronco. I lead segment marketing and strategy for Sci5, and I'm going to talk to you about the RISC-V revolution. I have been involved with the RISC-V community for about a year. But before that, I was at ARM for many, many years, and so I was watching RISC-V very carefully from the sidelines, including at one point leading the competitive strategy team at ARM, working out what do we do about RISC-V. And as the saying goes, if you can't beat them, join them. So here I am now. So what is RISC-V? So RISC-V is an open standard instruction set architecture. So the ISA is a critical part of any chip. It's the interface between hardware and software, and so therefore it's a really important part of what you do. Now, today, the dominant ISAs, x86 and ARM, are proprietary, so they're controlled by a single company, and that is holding us back in terms of what we need to do in the computer industry. So as Moore's law has ended and as the rise of AI is happening, there's more and more innovation that we need to do in terms of, in order to deliver the performance that we need from chips in the future. And the proprietary solutions are holding us back. And so RISC-V is changing all of that in terms of what we're offering with the open standard. Now, open standard interfaces are an accepted practice within the computing industry. You can see a number of these areas here. There has been, in the past, there's been proprietary solutions, but gradually an open standard has taken over. And that open standard enables both open source implementations and commercial implementations. And it's a range of different possibilities, but all based off that same common open standard. And the fundamental question is, why should an ISA be any different? And the answer is it shouldn't. There's no reason why an ISA should be any different to these other interfaces, and therefore an open standard model is inherently a better way forward. Now, if we look in a little bit more detail of what this means in terms of the business models and in terms of what you can do about it, here are kind of like the three main instruction sets that are out there. So firstly, with x86, it's pretty closed. You can get a chip from a couple of different vendors, but if you want to build your own chip that supports x86, you can't. If you want to build your own CPU, you can't, and you certainly couldn't build something open source based off x86. With ARM, the situation is a little bit better. So the nature of the ARM business model, the fact that they license the CPUs to many, many different chip vendors, means that you have a choice as an end device maker. You can buy chips from lots of different people that support ARM, so that's a good thing. However, if you want to design your own ARM CPU, that's really expensive. And as Qualcomm has recently found out, it's quite restricted in terms of what you can then do with that technology when you've designed it. And if you want to build a chip that supports ARM, then you only have one choice. You have to go to ARM. You have to go license a CPU from them. And if they're not building what you want, that's a problem. You haven't got any other options that you can have. But with an open standard with RISC-V, you can get everything. You can have many different chipset vendors building chips that support the RISC-V standard. If you want to design your own CPU, you can. Effectively, it's an open standard, so it's free and available for everyone to use. If you want to license a commercial core, then you can, and there's multiple different companies that are providing commercial IP that supports RISC-V. If you want to have an open source core, you can. There are also implementations of open source. And if you want to evolve the product, if you want to add instructions, if you want to customize what you're doing, these things are all possible because of the open standard nature of RISC-V. Now, you might be wondering why it's called RISC-V. And the slightly dull and disappointing answer is because it was the fifth design that came out of the University of Berkeley. Berkeley, through Dave Patterson of Patterson and Hennessy fame, pioneered a lot of the work around RISC computing in the early 80s, and they did several iterations of a RISC standard. And then for a couple of decades, they focused their research around commercial available products. But then in about 2010, they decided that that wasn't going to cut it. It wasn't enabling them to do what they needed to do to do research and innovation on the future of computing. And so they decided to develop a clean slate instruction set architecture and then to open it up. And the key people involved, you can see Andrew, Yunsuk, David, and Krista. And then That has then become released and made public in 2014, and it's gone from strength to strength in terms of the adoption and an enthusiasm behind it. And again, it's all based on the fact that it's this open standard model which is driving adoption. So who are Sci5? Well, who do I work for? So Sci5, the three of the guys, except Dave, so Krista, Andrew, and Yunsuk, once they'd released the open standard RISC-V, formed a company, Sci5, with the goal of developing commercial implementations of RISC-V CPUs. And today, we are the largest vendor of commercial RISC-V CPUs. Our business model is basically the same as ARM, in the sense of we license CPUs, and it's a mix of upfront license fees and then royalties per device shipped. But the critical difference here is that if you don't like what we provide, you can go buy from someone else and be compatible with the software. So you've always got choices. You haven't got that vendor lock-in. In terms of Sci5, we've got over 350 design wins, and that's with some of the biggest semiconductor companies in the world, including Qualcomm, Samsung, Google, Intel, Renesas, Microchip, long list of companies who are working with Sci5. And actually, you probably may not know this, but you're likely already using RISC-V in some way, shape, or form. If you have a phone that has a Snapdragon processor from Qualcomm that has RISC-V CPUs inside it, it's not the main CPU running Android, but it's one of the CPUs that are sort of controlling the system and managing the overall SoC. And there's lots and lots of devices that are using RISC-V already. We don't actually know for sure because a lot of this is going into different places and different people aren't reporting, but the estimate is there's tens of billions of CPUs, RISC-V CPUs, have shipped in devices. So pretty much anything that's a deeply embedded application, a lot of those have already moved to RISC-V or are moving to RISC-V. And what's exciting is that we're just getting to that phase where RISC-V in CPUs that are user programmable is just starting to happen. And so we're going to see a big increase in that over the next couple of years. From a software ecosystem point of view, there's been a big, big growth in the software ecosystem over the last couple of years, and the support from different vendors for what we're doing for RISC-V. One I'd like to particularly call out here is Android. So Google announced about a year ago that they were going to make RISC-V a first-class citizen, first-class architecture within their releases. And they said that Android 15, which is released next summer, is going to have full support for RISC-V. And they've just published a blog a couple of weeks ago saying that they are on track for that. So it's all going really well, and the support is there, and they've started to release certain builds with it available to developers. Yeah, so it's going according to plan there. And I don't know if you saw, but a couple of weeks ago, Qualcomm and Google announced that they were working on a wearable chip based on RISC-V. So future Wear OS devices using the Snapdragon Wear platform will be running on RISC-V, which is super exciting. But it's not just Android. That's just one example of many different open source projects, many different software, commercial and open source, which is building support for RISC-V. As you guys will know, this is a marathon, not a sprint. These things take a lot of time to mature, but we've seen really kind of rapid increase in adoption over the last couple of years. On that note, actually, I wanted to touch on a new organization that was announced earlier in the year. This was the RISE organization. So this was a new consortium that was established to drive, to accelerate the work on open source software supporting RISC-V. And this wasn't just formed by companies like Sci5 that have a vested interest in RISC-V being successful. The founding members included Google, Qualcomm, Samsung, Intel, MediaTek, and NVIDIA, who are all basically saying, right, there is a goal here to make commercial-grade open source software on RISC-V. And this is, and the focus here is very much on the high-end processors. As I said earlier, RISC-V has already established a really strong space in embedded processors and microcontroller type devices. And this is really about saying, okay, devices that run Linux, devices that, the high-performance compute devices, how do we make sure that commercial-grade software is available for those devices? And that's what we're doing through RISE. RISC-V International, so risc5.org, that is the standard-setting body. They are still very much responsible for all of the instruction set, the extensions, all of the standards around RISC-V, are managing the overall community, because there's lots of people involved in RISC-V, from academia through to commercial, from tiny microcontrollers to supercomputers. And the RISC-V International are very much responsible for managing that whole. But RISE is very much saying, okay, how do we make the Linux-based open source software commercially ready to be deployed on RISC-V devices? And so that's super exciting. And there should be an announcement next week about what Canonical is going to do on that one. I don't want to preempt that too much. So that's the organization. Now, one of the great things about RISC-V is it enables innovation. It enables you to create new instructions and to innovate and to do different things. And some of the detractors of RISC-V at this point will turn around and go, aha, that means that you're going to have a fragmented mesh. You're going to have lots of different products and it's going to become unmanageable, and that's not good. Now, the answer to that is it won't happen, and I'll explain in a minute why we can ensure that fragmentation doesn't happen. But before I get to that, I think it's really important to understand the difference between fragmentation and diversity. So fragmentation is the same thing done in different ways. So nobody benefits from the fact that the British drive on one side of the road and everyone else in Europe drives on the other side of the road. It just adds pain for vehicle manufacturers, it adds confusion for tourists. It's generally not a good thing. It would be better if we were all on the same side. In the same way, in the instruction set domain, there is no benefit in having two different ways of encoding half-precision floating point instructions. That will not help anyone. You have to have a single way of doing these things to make life easier for everyone. So that's an important thing. Diversity, on the other hand, is solving different problems. So a 747 and a bicycle are both forms of transportation, but they both have very different purposes. In the same way, in an instruction set world, you have 32-bit instruction sets, you have 64-bit instruction sets, you have 64-bit instruction sets for real-time processors, you have 64-bit instruction sets for high-performance servers, and having those differences make perfect sense. You get that with the legacy architectures like ARM and x86, and you get that with RISC-V as well. So diversity is a good thing, but avoiding fragmentation is critical. So how are we avoiding fragmentation as RISC-V? Really, there's two fundamental reasons. Firstly, nobody wants it. So everyone realizes what fragmentation will cause. Nobody wants a vendor lock-in. So if Sci-Fi comes up with some unique way of doing something that other people are doing in a different way, our customers are going to tell us they don't want it, because our customers want to have a single software base that they know that they can reuse across different implementations. And that's the second point, which is software. So investment in software is expensive. Nobody can afford to do all of the software themselves. That's why we have the whole open source movement. And in that context, you need to have a common baseline. So all of the open source projects are very clear that they only want to accept and upstream patches that apply to ratified standards. They don't want random extensions being included in the code base. They want to make sure that everything is based on the kind of like the ratified standards. So that's kind of like how fragmentation is going to be stopped. In terms of diversity, in terms of what we're doing there, then with RISC-V, you get a base set of instructions in terms of like the basic things that you need to do in a CPU. And then you have a whole load of extensions that are for specific functions. So maybe vectors or half-precision float or whatever. And then you have also, in addition to that, you have the opportunity to create your own custom extensions to do specific functions. Now, you can combine all of those in many, many different ways, which gives you a huge number of options. And that's great. And for embedded, that's kind of okay, because if you control the whole software and hardware stack, you can do what you like, and it's not a problem. But when you're trying to do something like a Linux distribution, you kind of need a bit more commonality. You need a bit more kind of like a consistent baseline that you're working with. And that's where the ISA profiles come in. So the ISA profiles are basically a standard set of extensions that are being defined by RISC-V and saying, right, these are the baseline that if you want to build a product that's for a Linux distribution, this is what it should look like. And that will evolve over time. So there was an RVA 20 version, there's a 22 version, 23 version, and so on. So in the same way that others' ISAs evolve over time as more capabilities get added, you expect to see the same from RISC-V. So the fact that these instructions are there is a really kind of good kind of common ground for everyone to work to. But then on top of that, you have, it's not just about the instruction set, it's things like how does it boot, how do interrupts work. You need a certain degree of commonality, and that's where the platform standards come in, and that's what work is happening now within the RISC-V community to specify, okay, beyond the ISA, what is it that is important? And this is very, if you're familiar with what ARM's done around System Ready and SBSA and those kind of standards, this is a very similar kind of concept, but for RISC-V. As an aside on this point, actually, I was having a chat to Mark yesterday, and we were talking, actually, wouldn't it be great if Ubuntu just works on every RISC-V platform, but also has the capability to automatically take advantage of any of the extensions that are available, any of the advanced features that are included in the products. And I think that's a really good vision. I think we want to get to the position where Linux distributions and software just work on any RISC-V platform, and you don't have to do a whole lot of a heavy lift just to get the software up and running. But then we also get to the point where we can take advantage of the diversity that exists. I'm not going, in the interest of time, I'm not going to go too much into the details of the ISAs, the extensions that have been ratified recently. This is just a snapshot of some of the things that have been ratified in 23. I think the main takeaway here, actually, is that RISC-V is now maturing. So the set of extensions that are now available are pretty comparable to what you might get from a legacy ISA in terms of the capabilities in the device. So if you take what's in, say, RVA 22, so the RVA 22 plus the vectors and the vector crypto, that has been, as an example, that has been defined by Google as the baseline for Android. So they're saying that is what we believe is the competitive baseline that we need in order to be able to do a commercial Android device. And so that is what is now kind of been focused on as a good baseline. And I think the same will happen around the Linux distributions as well, in terms of saying, right, what is the baseline that we want to support going forward as a competitive platform? Now, I'm sure some of you at this point are saying, oh, that's all great, this is all nice in theory, but where's my hardware? What can I get hold of? And the simple answer is that there is some hardware available today, and more is coming. On this slide, you've got a couple of different boards. You've got the Hi5 Unmatched from Sci5. That has actually been unavailable for a few months, but we've just got a new batch of them coming in, so that is now going to be available to order again. You've also got the Star 5 Vision 5 and the Polar Fire from Microchip, which also use Sci5 cores. But it's not all about Sci5. You've got the All-Winner core at the chip at the bottom that uses a core from Alibaba. And again, part of the benefit of RISC-V is that there's a diversity of supply and different vendors doing different things. What unites all of these cores, though, is that they all have Ubuntu support. So 2310 is available to download from the Ubuntu website for all 4 of these. So if you want to have a play, then go get a board and download the code. In terms of what's next, we have the Hi5 Pro P550, which we're going to be demoing next week at the RISC-V Summit, running Ubuntu on it, and that will be available in early 24. And then we have 2 more boards coming out from our partners, Eastwin and Softgo, who are doing chips that will come out later in 24 that are going to be compatible with the Android baseline that I mentioned, so RVA 22, and include a vector processing and vector crypto. So we're really excited about both of those. And then lastly, just a note in terms of Ubuntu and RISC-V. This community has been super supportive of RISC-V, so thank you to you all for that. It's been great to see what's been committed over the last couple of years. Ubuntu was the first distribution to support RISC-V in 21. As I mentioned, we're going to be shipping the P550 with Ubuntu pre-installed, and there's been a really strong engagement from the Ubuntu team and ourselves, but also with the wider RISC-V community, so that's been great. If you want to know some more technical details about where we are now and how to work with RISC-V on Ubuntu, how to work with Ubuntu on RISC-V rather, then Heinrich is going to be giving a talk in about an hour and a half's time, which I would encourage you to go to. Okay, so yeah, just to wrap up, I mean, the momentum behind RISC-V has really got to the point where I think it's unstoppable. And we will have the best processors, we will have the best ecosystem, and RISC-V will be present in every market that you can imagine over the coming years. The reason this is inevitable is not because the technology is that much better, although in some ways it is. It's fundamentally down to the open standard nature of the business model, which is driving demand from across the industry who really want to see RISC-V widely deployed and successful. So thank you. Come and join the RISC-V revolution.
Any questions? Microphone is coming this way, and then next question will come here and then over there.
Thanks. So what attitude do you have towards the possibility of whether there is lock-in through diversity? And what I mean by this, if you look at the early IBM compatibles, they all had like different standard modes, and Hercules and CGA were shipped by IBM by default. But if you then went and bought a 10D, then you were able to play on a cheaper machine like the better 10D graphics modes, and you would want to continue buying 10Ds to not downgrade. Is there a danger of this kind of vendor lock-in you're seeing with making extensions so like readily accessible for hardware manufacturers?
I mean, I think it's always a possibility. I mean, the nature of the way RISC-V is working means that there's more things happening, and people are more free to do different things, which means you're not controlling it in that way. I think, as I say, there's powerful forces that mean that people don't want that. And the work that we're doing in RISC-V International to try and sort of define the platform standards and then align the distributions around saying, okay, this is what is supported, I think will help a lot. Google, for instance, have said they're never going to support less than RVA22 vectors and vector crypto. They're saying if you want to go do it yourself and you want to go build a random Android build and hack it onto earlier hardware, then that's fine, you can do that, but it's never going to be supported in mainland Android. And so I think it's that kind of desire to avoid that which will prevent it. But you're right, it's not, because RISC-V is not controlled and managed in a way that others are, there's always risks of that. And I think we just, as a community, we need to be careful to make sure that we don't add unnecessary blockers and barriers to innovation.
Thank you.
There. So, hi. All right. Yeah, so I liked how you mentioned that like RISC-V is kind of making its way from like microcontrollers up into supercomputing. And so one thing that I did want to ask was like, have you seen a lot of demand from like these HPC institutions to use RISC-V? Because I know a lot of places are still, running these traditional big x86 machines. So I'm just kind of wondering, what's the demand look like, and how do we incentivize more institutions to kind of shift towards this architecture?
So we're seeing huge demand, actually. So maybe not necessarily sci-fi, but RISC-V as a whole is seeing huge demand. And I think the reason for this is that a lot of the particularly national sponsored initiatives are very sensitive that they need a long-term strategy. And so that's what RISC-V gives them. It gives them that long-term strategy where they're not going to get locked in and they're not going to get restricted and they're not going to run into export control issues. They can control their own destiny. So, I mean, pretty much anyone who's investing in HPC is investing in RISC-V, I would say, and it's just a question of how long that takes and when you're going to start seeing things. But within the RISC-V community, the HPC special interest groups are a really active part of that community.
That was a very politically correct answer. Over there.
Yeah, come and see me afterwards if you want the unpolitically correct.
Hi. What would you say was or is going to be the tipping point for RISC-V adoption? Is it one of those extensions that were just approved, maybe the crypto or vector? It feels like there were a lot of extensions approved in 2023. Are we in a turmoil right now and will this stabilize, or how do you see
No,
it?
I think actually there's a lot of stuff that's been happening over the last couple of years, kind of to catch up. Do you know what I mean? So to make it, as I say, to get to a position where, from an instruction set point of view, what we have is comparable and competitive with the latest from other vendors. I think in terms of a tipping point, I mean, I feel, it feels to me like it's very soon. It feels like there's been a big increase in momentum over the last couple of years, and the news flow in terms of people committing to it is getting increasing. I think it's one of those things. I say I spent many years at ARM, and I was looking at ARM servers for many years. And there was years and years and years where everyone was saying, it's not going to happen, nobody's ever going to do it. And you had these failures, and you go, well, they failed, it's never going to happen. And then suddenly it happens. And now we're in a world where some analysts are saying, right, 50% of the server market's going to ARM. RISC-V in what I would call the apps processor, the Linux market, is going to be the same. Do you know what I mean? It's going to suddenly reach a point where devices are out there that are good, and people go, okay, right, this is now a viable option. We're now going to move, and that what triggers that is hard to say, but you can certainly see that happening over the next couple of years.
Yeah. So I like RISC-V, but if I was doing my job, I would have never heard of it because I'm writing Python.
Yep.
At the most, if I'm writing something in lower level language, I just say, oh, cross compile to this architecture. Should I know about RISC-V, like from the ISA, from the assembly code? Is there something interesting there? I mean, is it fun there to look there? Hey, later on, stop writing Python, directly write the RISC-V assembly?
I think it depends how you like to spend your weekends, whether it's fun or not. I mean, I think that part of the way. So at one level, no, I don't think you need to care. Do you know what I mean? If you're writing Python, other people will care about a lot of these things. But I think back to what I said right at the beginning about the end of Moore's law and the rise of AI means that increasingly we're going to have to think more carefully about how hardware is architected and how software and hardware work together in order to drive performance. So yeah, at a basic level, the RISC-V instruction set, it's just an instruction set. It's not that exciting, but it's what you can do with it and what you can do with it in terms of hardware, software, co-design that I think will become very exciting in the future.
One question at the back there, I think with the front, and then we'll go for break.
Do you know anything about the mainline Linux kernel support? You mentioned Android and Ubuntu from a certain version number, but you know, is that is that on top of mainline Linux? They're doing their own customizations,
Yeah.
or is it?
Yeah, no, it is. I mean, I think so. What you see is that pretty much all major open source packages, including Linux, have increased support for RISC-V over recent years. The finer details of that, would come and have a chat to me afterwards. But yeah, just in principle, it's not something Canonical is doing independently. It's part of a broader move with support across all of the Linux community. And it's just Ubuntu has been really positive in terms of releasing distributions for specific hardware. Hello.
Hi. With profiles building on profiles, what's the balance between leaving old hardware behind and risking that RISC actually becomes CISC?
It's a good question, actually. So I guess in terms of leaving stuff behind, it's always a balance, isn't it? So if you look, say, in the ARM world, ARM adds new instructions every year to their architecture. But from an app developer point of view, app developers are stuck on kind of a 10-year-old ISA because actually you can't migrate across because you can't leave a whole load of apps behind. So it's a delicate balancing act in terms of that. In terms of your question about RISC becoming more CISC-like, yeah, that's an interesting angle because as we add things like vector instructions, matrix instructions, add more capabilities into the device in order to try and drive that performance, these things are getting more complicated, but fundamentally RISC-V starts from a cleaner position and is therefore probably better placed to deal with some of these challenges as we go forward. We haven't already got 20 years of legacy built into what we're doing. In 20 years' time, we will have that legacy problem. But we're in a better starting position for where we are now.
Right. So before I let you go, anyone here who's involved in actually porting Ubuntu or Linux to RISC-V? Heinrich is there, and so there you go. You know who to go and talk to. If you actually, both of you could stand up, maybe so that everyone knows your face and can come and talk to you if you're interested. There we go. You have 3 people there. John, that was amazing.
Thank you.